So welcome back friends for a another class on quantum field theory and quantum entanglement. We have been looking at uh, uh, the quantization of a free scalar field, and we have considered a real scalar field. Now okay, yeah, so you can see that uh, uh, pi of xt and pi of xt, these are the two things essentially which we have the conjugate momenta, and then the procedure we used was that we imposed canonical quantization conditions which we define in this particular fashion. Essentially these are called equal time canonical commutation relations, and what we said was that phi should be considered as a dynamic collection of dynamical variables. So we can write phi as a collection, essentially a Fourier transform of that essentially in momentum space. So you can write pi tilde of k and t in terms of phi of xt, and same thing of pi tilde of k of kt to be in terms of e power minus kx pi of xt essentially. So you take the Fourier transformation, and then you get the inverse Fourier transformation. And so what we started was that the dynamical field what we started as a scalar function now is now being considered in terms of a bunch of dynamical variables essentially. So it's a this is a major step in what we are looking at, and then we have some consistency conditions in terms of the realness of the scalar field essentially. Then imposing the Heisenberg equations of motion, which is nothing but the Klein-Gordon equation of motion, you can write down the solutions, and the solutions will give you this particular general solution essentially in the momentum space. So which we have seen already essentially. Okay. So for each mode we have the Klein-Gordon equation which is solved in terms of and in terms of plane waves, and so you get the plane wave solutions in the momentum space for the Klein-Gordon field. With this, putting it back into this, one can solve for phi of kt, and so we end up having a bunch of expressions again in terms of pi 1 of k and q pi 1 dagger of q. Again we get back the momentum space canonical quantization conditions which give you in this particular fashion essentially. So these are your momentum space canonical quantization conditions. So now this the moment we see these canonical quantization conditions, we can immediately revise ourselves to your harmonic oscillator, okay, which we have done in lecture 3. Essentially we have seen that in the lecture 3 we can re-express your the wave functions in terms of simple harmonic oscillator. We have revised that essentially, and then we see that you can express the annihilation operator in terms of phi 1 of the wave function, and so you follow the complete expressions in terms of the creation and annihilation operators for the real scalar field in this particular fashion essentially. So pi of xt is given in terms of a of k e power kx k, which is a plane wave part, and then a dagger which is given by this particular thing. So this is you have pi of xt and the conjugate momentum field in terms of these annihilation operators and creation and annihilation operator for a single scalar field, for a single real scalar field. So with this we have okay motivated that the canonical quantization conditions in terms of pi of xt and k pi of x and equal time commutation relations which we have written down earlier essentially can be re-expressed in terms of is essentially equivalent to writing the fields pi and phi of xt in terms of these series of harmonic oscillators in momentum space a of k and a of k, a dagger of k and a of k bar and a dagger of k bar, okay, and in this particular fashion, and this is true for a, and now imposing harmonic oscillation like conditions for each momentum mode, okay, and that is your solution of your canonical quantization essentially, that is your solution of the canonical quantization. So we will now dive into the, we will now continue seeing the properties of this and dive into the next step essentially, a continuation of the canonical quantization and properties. So today we continue with canonical quantization. Okay, and then we will do it for multiple fields and so on. So essentially what we have done is essentially that the entire field is started with again, so started with uh, to write it uh, in terms of this thing essentially. So you started with a classical field, okay, phi of xt, and it wrote the conjugate momenta pi of xt, which we know we can derive it from the Lagrangian essentially. Then we upgraded this into linear operators. So these are essentially what we did by defining them to be phi cap essentially, and then we wrote a phi cap essentially, and then impose the commutation relations. Which are essentially phi of xt, pi of y. At the same time is delta cube x minus y. Okay, 1 second, let me write it down. It's equal to delta cube x minus y. So this what is happening? So we essentially started with a classical field, wrote the Hamiltonian equations of motion, expressed the Fourier a bunch of, we considered phi to be a bunch of dynamical variables, quantum dynamical variables, and then we expressed it in terms of the Fourier transform, and so we ended up with this. And in doing this, okay, we ended up with a bunch of harmonic oscillators for each momentum mode essentially. So what we have seen is that for a real scalar field, each momentum mode acts like a harmonic oscillator, and each momentum mode acts like a harmonic oscillator, and this gives you a harmonic for each momentum mode satisfying harmonic or simple SHO commutation relations. So this satisfies the simple harmonic oscillator commutation relations, and so you end up having a bunch of this particle meaning. Now each of this commutation relations, so this tells you that this is a particular particle essentially. This tells you this is a particular particle, each state is a particular particle. Okay, so let me continue with this. So we have written again phi of x. Okay, let me continue with this. So the full form again, let me repeat it. So you can actually start with this. Okay, pi of x is equal to integral d cube of k. I have written it in this one. Some a of k fk. I just wrote it down in terms of fk of x. This is nothing but your exponential function, this plane wave part. So just let me rewrite this entire thing in this particular fraction. So what we have is in terms of a creation annihilation operator, and then its dagger is nothing but your um, if you want, this fk of x is nothing but your plane wave part by 2 pi cube 2 omega k. Okay. So this is exactly the same notation as what we used, and then you have a and a dagger will appear because in the HC part essentially a is the creation operator and a dagger is the annihilation operator. Now you write down what we wrote down was pi of x. So minus I omega k a of k fk of x plus hc. Okay, the same fk essentially. Somehow, yes, too many dots on this. Okay. Okay. Now the point I want to make is that I motivated this by saying that I got this expansion because I wrote down the Heisenberg's equations of motion, and then solve this in terms of this particular thing in momentum space, and so I ended up having this kind of an expansion essentially. But you can say that I start my field to be the quantum field to be a series of harmonic oscillators. I can really start with this particular thing and then re-express your field in terms of this harmonic operator. This could be your starting point, and here imposing then a canonical quantization conditions will end up giving you the harmonic oscillator conditions will end up giving you the canonical oscillation conditions also. Okay. Okay. So now this I promised you that I will tell you the difference between how we started with the Klein-Gordon field, okay, when we did the Klein-Gordon equation essentially, and what is the difference between the Klein-Gordon field and the Klein-Gordon equation, the particle essentially. Okay. Now this is by definition a multi-particle system essentially. By definition, this is a multi-particle system. This cannot be thought of as a single particle like what we did in the relativistic quantum mechanical picture is essentially that we considered one single particle as a wave function, and then we saw that there is always an antiparticle wave function associated with it. Here we are talking about a real wave, real particle essentially, a real wave function, a real scalar field. So the difference is that it is no longer there are earlier times people used to call it as a second quantization, but now in the modern language what we consider it as a scalar function. It's a scalar field and it's a real scalar field, and this real scalar field is being expressed in terms of, can be expressed in terms of series of harmonic oscillators such that you can have a mode expansion. Okay, you have a mode expansion into this. So, this is inherently a multi-particle system, cannot be considered with the relativistic wave function of the Klein-Gordon field, essentially Klein-Gordon equation essentially. So, this is not relativistic quantum mechanics we are doing here, is essentially a multi-particle system to begin to already do it essentially. So, to use uh, uh, the the relativistic quantum mechanics picture, in terms of a single particle wave function for the Klein-Gordon field, wave function for the Klein-Gordon equation is inherently wrong, and it leads to several problems. It leads to several problems. It leads to several problems. So, we should not concentrate on that, but the correct way is to consider phi of x t as a relativistic quantum field which here we write it in terms of series of harmonic oscillators for a real scalar field essentially. Okay. Okay. So, now let us now continue the momentum operator and everything. Essentially we will this so the A of k and A of k dar, we know that they follow the harmonic oscillator formula, okay, k prime or q essentially. I think we used q earlier. Okay. Q, the commutation relation is equal to del cube k minus q, A of k, A of q is equal to A dagger of k, A dagger of q is equal to 0. These are the same commutation relations as for the harmonic oscillator, but now there is a mode. For every mode there is a separate creation operator and an annihilation operator. What does the Hamiltonian look like? K 1 by 2 A dagger this is this is if because we revised the harmonic oscillator, it is very obvious that this is the thing. It is just the harmonic oscillator Hamiltonian, but with the main difference is that A dagger, which is will now depend upon k. which is the momentum mode essentially. So there is a frequency dependent for every momentum mode there is a different frequency and so on. You can also do the momentum operator. So this is nothing but d cube k 1 by 2 a k a dagger k plus a dagger k a k. Okay. So this is these two are the important equations. Essentially we know that we can write down so these are essentially like your independent harmonic oscillators essentially with the momentum operator. You can discretize it, you can you can discretize it, you can think in terms of so this is like if you say let's discretize them instead of continuous k values we can go into discretized momenta. So let's say that if we discretize it this becomes this, once if we discretize it just to k. So the point is that instead of k being a continuous variable make it a discrete variable. I will come to that in a minute, we can do more about it. So in that case the commutation relations will become ai a j dagger delta I j. So instead of each k you have k1 k2 k3 k4. So make it a descriptive k1 k2 k3 kn, n tends to infinity. So in that case you can remove the k and call it as a1 a2 a3 a4 and so on. So and so you have this relation. So you have the same relation ai aj is equal to ai dagger aj dagger 0. So the Kronecker delta, okay, so delta ij is replacing delta k minus q. Okay. This is what is this is replacing essentially. So make it a discretized variable and then so now the system becomes much more clearer. The Hamiltonian can be written as sigma I is equal to 1 to n, the same thing essentially 1 by 2 omega instead of k and everything we are write it in terms of I. Oh, okay, right, ai dagger plus ai dagger ai. Now this is a Hamiltonian of a series of harmonic oscillators, okay, running from 1 to n essentially. So it is a Hamiltonian of series of Hamiltonian of n harmonic oscillators. So it is a bunch of harmonic oscillators. So it becomes much more concrete what I was saying you earlier essentially. Now we had to give it some interpretation. What is this harmonic oscillators meaning essentially? What is it? Okay, each harmonic oscillator has some n number of states essentially. So large number of states, and so what is this space which we are building of this bunch of harmonic oscillators? So we have this huge number of harmonic oscillators and we are building a Hilbert space of this. So what is this space we are building it essentially? Okay. So before that let me introduce you, so for that I need to introduce you some things essentially. So I introduce you the number operator. I need to write slowly, I think. Yeah. So the number operator n is equal to a dagger a. So the Hamiltonian would be essentially that it is half omega a dagger a plus a dagger. So this is equal to n plus half omega. So but you have, so generally what happens if there is a one state essentially for I is equal to 1. So for I is equal to 1, and this is true for I is equal to 1, and the Hamiltonian is for one state. For one single harmonic oscillator we have this particular thing. Okay, for one single harmonic oscillator we have n plus half. This is well known to you essentially. The number operator and the ground state is equal to 0 and n is equal to 1, 2, 3 and so on. So essentially, so n is equal to 0, 1. So the number operator, what does it do? It acts on a state n, gives me what is the number of states which is associated with it essentially. Okay, so now this n, okay, now we have, what does a dagger operator do? This also we have taken essentially that a dagger operator takes a state n, gives you root n plus 1 n, a of n gives you root n minus 1. Oh no, this is an, I think it's an error here. Okay. So the number operator tells you the numbers here essentially, and n is equal to 0, 1. So now this a dagger takes you one step above, so it increases the state by 1 and it's a raising operator. All this we know essentially. So here it is a lowering operator. This all I think we already covered, meaning we revised in the harmonic oscillator case essentially. So the energy operator, the Hamiltonian energy operator En for the nth state is essentially nth state is equal to n plus half h omega. And the lowest energy state is equal to E0 is equal to half omega 0 point energy. So this is just a revision of your harmonic oscillator for, so for 1 is equal to 1 essentially. How do you obtain the nth state? You obtain the nth state. This is, oh, you obtain the nth state by acting a dagger several times on the 0th state. All this is well known essentially, all this is well known. Now, so what we need to do is that now what happens if you have the same system, this is for I is equal to 1. So this is simple harmonic oscillator in quantum mechanics. So this is what we have done already. So when we discretized k, okay, we have large number of these harmonic oscillators for each k. So k is equal to 1, k is to 2. So for n is equal to I is equal to 1, we just revising what it is. Now for several I, that means I not equal to 1. So the Hamiltonian is given by I is equal to 1 to n omega I ni, it's a vector now, plus half. Now ni cap will be ai dagger ai. This is your, so instead of one single harmonic oscillator you have bunches of harmonic oscillators. So this is what it is essentially. So what is the ground state look like essentially? So you can, okay, what is the ground state look like? So you have a ground state O, which is direct product to ground state of all the n ground states essentially. Okay. So the vacuum state is annihilated by so this any of the operators. So meaning you can have ai acting on 0, this is the left hand side essentially, is equal to 0 for all I where I is equal to 1 to n. So this is of course this is a discretized way of looking at it, but what we have is actually it's a commutator, we have an continuous thing. But let us just understand so that we get a picture in terms of a discretized thing. So how does the state n state look like? N state essentially, okay. So the energy, okay, the n state is essentially, so n1, okay, okay, n1 and 2 and n is equal to n1 direct product n2 direct product n3 so on, so nn, okay, so on. So now each n1 is given by application of its a dagger operator on the vacuum. So this is acting n1 by root n1 plus 1 0 n1 factorial factorial times a2 whole dagger acting n2 times by root n2 factorial acting on the vacuum state, and so on, so on, so on, so on, so on. So what we have essentially seen is that in the discrete picturization that the series of harmonical oscillators creates a vacuum state itself is a complicated vacuum state where any AI will annihilate the vacuum, because any AI will annihilate the vacuum. So if you have several AIs, this bunch of harmonic oscillators, okay, and then you can create a state by acting it is because it's a any, and so you can have a state in which only one of them is switched on essentially. You have one of them is switched on. So one and one is switched on, and then it creates one positive state, and there could be another say. So, there is a bunch of these states which are all in direct product with each other, essentially which are all in direct product with each other. Okay. So, this gives you the vector space of this one. This vector space is uh, complicated, and so what we have is total n is equal to sigma I is equal to 1 to n ni. Okay. And I will just write down one particular thing which is interesting. Energy of the nth state is I is equal to 1 to n ni plus half omega I, and in particular for the ground state is ground state. Okay, hope you have got it, and I will stop here. I will continue in the next class essentially. Okay, I will continue in the next class. So, okay, thank you very much.